For decades, the diamond industry relied on a single physical bottleneck: geological time. Natural diamonds require billions of years to form under extreme pressure in the Earth's mantle, followed by intensive extraction from deep open-pit mines. That multi-billion-year timeline is now being collapsed into weeks. Engineers are replicating the mantle's environment within sterile, controlled laboratories to produce rough stones on a manufacturing schedule. This process focuses on the crystallographic baseline. Lab-grown diamonds consist of pure carbon crystallized in the isometric cubic system, making them chemically and physically identical to their mined counterparts. Professional classifications reflect this material reality. The U.S. Federal Trade Commission recognizes these stones as real diamonds, possessing a 10 on the Mohs hardness scale and the exact refractive indices required for brilliance. Material science has effectively decoupled the gemstone's chemical composition from the artificial scarcity of its historical pricing model. The economic results are stark. The lab-grown market, valued at $1 billion in 2020, is projected to scale to nearly $109 billion by 2035. This signifies a permanent movement away from finite resource extraction toward a model of scalable, technology-driven manufacturing. The first manufacturing method, known as high-pressure, high-temperature, or HPHT, approximates the Earth's mantle through immense mechanical force. Inside a multi-anvil press, a diamond seed sits in a capsule with a graphite source and a metal catalyst. The machine applies 5 to 6 gigapascals of pressure, while raising the temperature to 1600 degrees Celsius. Sustaining this extreme environment requires constant energy input, averaging 28 to 36 kilowatt-hours for every carat produced. Under these conditions, the carbon dissolves into the catalyst and crystallizes onto the seed. The resulting rough stones typically form cubo-octahedral crystals and may retain tiny metallic inclusions from the catalysts used in the melt. This replication effectively mass-produces industrial abrasives, small, brilliant Meili diamonds, and fancy-colored stones, specifically yellow and blue varieties. HPHPT functions as the industry's heavy lifter, focusing on high-volume output rather than atomic-level precision. Chemical vapor deposition, or CVD, utilizes a different approach. Instead of crushing carbon, it uses chemical reactions to assemble diamonds atom by atom. CVD occurs inside a vacuum chamber at significantly lower pressures, roughly 1 to 4 gigapascals, and moderate temperatures ranging from 700 to 1200 degrees Celsius. Hydrogen and methane gases are introduced into a vacuum chamber. Microwave energy generates a plasma cloud that breaks the molecular bonds, releasing pure carbon atoms. These free atoms deposit onto a tabular diamond seed, building the crystal structure layer by layer with high precision. While CVD requires more energy, up to 143 kilowatt-hours per carat, the reactor equipment is smaller and less expensive to deploy than HPHT presses. This level of atomic control has made CVD the primary method for producing large, gem-quality stones and specialized semiconductor wafers. These engineering profiles have created a concentrated global production chain centering on 3 primary nations. China maintains a massive lead in HPHT scalability. Henan Province utilizes its historical infrastructure in super-hard materials to control roughly 60% of global lab-grown output. India has captured the CVD expansion phase. The city of Surat alone houses an estimated 4,000 to 6,000 active CVD reactors. State policy accelerated this growth. By removing taxes on the diamond seeds required to start production, the Indian government rapidly expanded its domestic manufacturing capacity. This reactor growth integrates with India's existing monopoly on global diamond cutting and polishing, creating a vertically integrated supply chain. The United States focuses on the high-end ceiling of CVD technology, leading innovation in single crystal growth and advanced material applications. Geopolitical manufacturing capacity and aggressive state investment now dictate the global diamond supply. This chart illustrates the drop in retail pricing as manufacturing efficiency improved. In 2016, a high-quality 1.5-carat lab diamond cost over $10,000. By early 2026, that price fell to roughly $1,100. Current benchmarks show the widening gap. A 1-carat lab-grown stone now averages between $725 and $1,500, while a comparable natural diamond commands between $4,000 and $8,000. Lab-grown diamonds now follow the economic patterns of technology hardware. As manufacturing scale increases, unit costs continually decline, breaking the model of scarcity. These declining costs have triggered the carrot upgrade effect. Consumers are using the same budgets to purchase significantly larger stones. The results are measurable. The average size of a lab-grown engagement stone rose from 1.31 carats in 2019 to 2.45 carats in 2025. Demand is increasingly concentrated in younger demographics, with 66.7% of Gen Z engagement ring buyers now opting for lab-grown stones. This shift is supported by verifiable sustainability metrics, including a zero mining footprint and significantly lower water consumption than traditional extraction. The market has separated. Natural stones now compete on the emotional premium of rarity, while lab-grown diamonds compete on utility and objective material quality. Lab-grown diamonds are rapidly normalizing in the consumer market, transitioning from a specialty item to a standard commodity. Major jewelry brands are scaling this transition by moving toward production models powered by 100% renewable energy. However, the most significant growth is happening in advanced industry. Diamonds possess extreme thermal conductivity and hardness, making them essential for high-performance applications. Pure CVD diamond wafers are currently being integrated into semiconductors, where they bypass the thermal limitations of silicon. This carbon technology is becoming a foundational component in quantum computing nodes, high-speed thermal conductors, and advanced optics. These industrial applications, extending far beyond jewelry, are the primary drivers of the projected $109 billion market valuation. Engineering scarcity out of the carbon supply chain has integrated the diamond into the foundational infrastructure of the next technological age.